All right, we are back, and good morning to you all. We shall start our discussion very shortly. All right. Again, during the class, if you encounter any issue, please raise a question in the live chat. I shall be definitely answering your queries. Okay. All right. So in today's agenda, we have signal flow graphs, and we shall discuss what they are and how to actually construct a signal flow graph out of a block diagram. And from that, we shall figure out a one-step method to calculate the transfer function of a whole system like that in a single step. Right? All right. And then we shall solve the problem that I gave you in our last discussion as a homework problem. We shall tackle that problem as a block diagram reduction with block diagram reduction technique, and then we shall see how we can apply a signal flow graph technique on that to actually calculate the overall transfer function. So this is what we have in today's agenda. All right. So we shall start in just like 1 minute. All right. Again, whenever you have any difficulty understanding something, we shall introduce a few new terminology today. So if you find something difficult while I'm discussing it, make sure to raise a question. I shall be answering your queries. Right? All right. So let's get to it. All right. So I just have copied something from our last discussion, from our last stream. We did block diagram reduction on a slightly complicated system, okay, in order to figure out the overall transfer function, in order to remove the level of abstraction and get an overall transfer function out of everything, right? We did block diagram reduction. So something you noticed from that class is that the block diagram reduction technique is not unique, in a sense that if you give me a block diagram like this one, I might proceed to solve this in a particular way. You might proceed to solve this in another way, right? So the technique that you might want to use could be different from mine, right? And that's quite usual, because block diagram reduction technique does not give you actually a specific way for solving the block diagram, right? For reducing the block diagram. Instead, it tells you that if you remove a certain branch from here to there, then you have to do some computation like this. If you combine two blocks like this, then you have to provide certain computation like that. Then this is the equivalent block. So block diagram reduction technique gave you the equivalent blocks for some primitive block configurations, right? So block diagram reduction technique essentially gave you what to do when you have two cascaded blocks, what to do when you have two parallel blocks, and what to do when you have two feedback blocks. And with that, it gave you a few more techniques related to signal integrity, okay, and that you could use to figure out if you move this branch from this place to this another place, what to modify in the associated transfer functions. So that is something you actually learned, right? So for the most part, block diagram reduction was an ad hoc technique. Ad hoc means you did what was necessary, right? Ad hoc means you did what was necessary, essentially, right? So so you did what felt right at that moment, right? So block diagram reduction for the most part is an ad hoc technique. There is no systematic way of actually doing a block diagram reduction. You can do it in your own way. I can do it in my own way, right? So that way, this methodology is not unique, and for that reason only, this block diagram reduction technique cannot be directly implemented as a computer program, right? I mean, you can do it, but you would have to go through quite a lot of hassle in order to actually implement a computer program that can do block diagram reduction through block diagram reduction technique, because this is not systematic. Anything systematic, however complicated, can be implemented using with a computer program, right? And nowadays, with the advent of computer programming and advent of computers, we try to implement everything using a computer, right? All right. So with that aside, I just copied what we did in our last class. So this was our transfer function that we actually discussed in our last class, and this was the overall. This was the system that we actually reduced in our last class, and this was the overall transfer function, right? So we actually went through a lot of hassle. Okay, so we first brought this in this side to this side, and then we combined these two blocks as cascades. Then we brought this branch to the right hand side, and then we did considered a feedback loop here, and then we considered a cascaded block, then we considered a feedback, then we considered another feedback, and after doing all those computations, we eventually landed on this solution, right? So this was the overall transfer function. So this was, I mean, the top level abstraction. So if you are looking at the input and the output, and namely the input is X here and the output is Y here, if you are just looking at these two, then this was the transfer function. Okay, and some of you are saying that whether I checked your homework or not. I was actually caught up with a few things, so I couldn't check those, but I will definitely do that. All right. Again, we shall be actually solving those problems today, so you can actually verify your workings. With that said, there are a few things I need to tell you. The first thing is that in signal flow graph, of course, as the name tells you, signal flow graph is a graph. But don't take the word graph as a plot or something like that, right? So maybe in our schools, we kind of gotten used to hearing the term graph used as a synonym to plots, right? But this is not what we are talking about here. Graphs are essentially something called, also known as networks. Okay, graphs are essentially a graph theory. So here, whenever we are saying graph, we are actually talking about graph theory essentially. Okay, and graphs are essentially something like this. It's a part of abstract algebra actually. Okay, and here what we talk about certain nodes and how they are connected. So for example, I have two nodes, for example 1 and 2, for example, and if they are connected like that, then we say that it's a graph in the context of graph theory. Imagine these are two cities, for example. Okay, and we have a connection between city number 1 and city number 2, and we have a connection between city number 2 and 3. Then if I draw it like that, then what we have done essentially, we have constructed a graph, right? So this is a graph. Especially this is called an undirected graph, because if this line here or this curve here is denoting a path between or a connection between node 1 and node 2, okay, or city 1 and city 2, then this path is kind of unidirectional, or rather this road is kind of unidirectional, which means you can go from this direction to you can go from this direction to this, and also you can come back in this direction, right? So this is kind of undirected, right? But it could so happen that this road that I have here drawn, okay, is kind of directed. So you can only go from city 1 to city 2, but you cannot come back, for example, say. Okay, you can only go from city 2 to city 3, you cannot come back in the same way. So things like that. Okay, so if I draw examples like that in this way, then what we have essentially is a graph, right? Is a graph, right? Now maybe something like this. I'm drawing another graph, another line here, another curve here. All right. All right. So currently, say I am at city 1, for example, and I want to reach city 3. So I have two possible ways in which I can actually reach city number 3. Okay, I can actually go through city 2 and then to city 3, right? Because I have a way from city 1 through city 2 to city number 3, right? Or I can go from city number 1 to city number 3 directly. Now imagine, with that said, if I ask you which set of roads are you going to consider? Are you going to consider this way or this way? Of course, you're going to probably say, okay, I'm going to just take the shortcut, right? I'm going to directly go from city number 1 to city number 3. But what if I told you something else? What if in addition to the path like that, I told you that going from city number 1 to city number 2, the cost for that path is, say for example, say 10. Maybe it could be 10,000 rupees, maybe it could be 10 something, right? Just say it's 10, right? And the cost from this path to this path is, say for example, this point to this point, okay, is say 5. And say this is 20. Now of course you can start from city 1 and reach city 2, city 3 directly if you pay this much. But if you take the long route and start from this one, city 1, and go through city 2 to city 3, then you are paying less. Now if I ask you, okay, which one of these set of roads are you going to take? Yeah. Someone is saying 10 lakhs, right? No. Anyway, so now if I ask you, which one of these, which set of paths are you, roads are you going to choose in this case? Of course, the answer would be very simple, right? If I'm talking about the cost, probably I'm going to go through city number 2 because that's going to give me a way of traveling with the minimum cost, right? I'll be reaching my destination, but with the minimum cost. You understand the agenda, right? All right. So what we essentially have is called a graph. This is essentially an example of a graph. And especially this is an example of a directed graph. Okay, so directed graph means you have certain direction in the roads that I am drawing actually. Yes. So essentially what happens here, if I am talking about the cost, then this is the shortest path, right, in terms of the cost. Okay, all right. So with that said, let me clear the nomenclature here. So these points that I have drawn here, these points here are known as nodes or vertices. Nodes or vertices, or a singular would be node and a vertex. Okay, so these points are nodes or vertices, and singular is node and vertex. So this is a vertex, this is a vertex, or this is a and this is a vertex, or namely this is a node, this is another node, this is another node. So node 1, node 2, and node 3. All right, and these roads that I have drawn, okay, are known as edges. So these are edges, right? All right. So essentially what we have as a graph is a set of vertices and edges showing how they are connected. So in terms of graph theory, what a graph essentially is a set containing all the vertices and another set containing all the edges that connect individual vertices, right? So essentially the graph would be something like a set of nodes. For example, of course, how do you write down a set? Just like that, in a raster form you would write, say I have, so this is for example, so this is how you actually represent graph as a set of sets, right? Because essentially this is a part of abstract algebra where set theory actually lays the foundation, right? So n is a set of nodes. So you have node number 1, node number 2, node number 3, and they can be named differently, right? You can call this city 1, city 2, and city 3. Essentially nodes will have the names city 1, city 2, city 3. These are just names, right, associated with it. And then you have a set containing tuples like this, and you are familiar with tuples, right? So I am writing 1, 2. This indicates there is an edge between 1 to 2, and the edge starts from 1 and ends up at 2, and then you have another edge from 2 to 3, and then you have another edge from 1 to 3, right? All right, and then you would have a set of weights. This is a weighted directed graph. as a very if I become very specific here, this is an example of a weighted directed graph. Okay, so why directed? Because all these edges have directions, right? And why graph? You know that this is the terminology we use. And why weighted? Because all these edges have a certain weight associated with it. The weight could be cost, the weight could be time, anything, if these are roads, for example, right? And we have another set denoting the weights. For example, say we have set W denoting the weights, and here the weights are so they are associated with the edges. For example, okay, we denote the age weight for the edges. For example, this edge, so edge 1, 2 has a weight of 10, and this edge has a weight of 5, and this one has a weight of 20. So like that. So what we essentially have is a graph. So for a directed weighted graph, we need the set of nodes or set of vertices, set of edges. Edges are basically connections between nodes, and here for a directed graph, directed connections. So you can start from 1 to and go to 2. You cannot come back in the same path using the same edge basically. So the direction would give you the direction in which you can actually go. And these are the set of weights. Set of weights are directly associated with the edges, right? All the edges, and especially for the example here, we have a road and like that. Right? Now the thing is, graph theory is pretty applicable in many situations where the representation can be converted to a set of edges and set of nodes, right? Or edges are sometimes also known as branches. I shall not use the term branches, but yeah, they sometimes are called branches, right? Now, a popular example of something that can be converted to a graph like that, a set of nodes and set of branches with weights in them, is electrical circuits, right? Right? Electrical circuits essentially can be easily converted into graphs like this. Very easily, you can understand that if I draw an electrical circuit, you essentially have nodes, right? You know what nodes are, right? Okay, so you can essentially draw nodes, and all the branches through which current flows through certain electrical elements, they can be converted into edges like that in a graph. So between two nodes, so for a circuit, this could be one node, this could be another node, and this one could be a branch connecting these two nodes, right? Very easily understandable. And here this number could be representative of the impedance of that particular branch or something like that. Okay, that way a circuit is pretty easily representable in terms of a graph. All right, and I believe you studied how to apply graph theory to solve generalized electrical circuits, right? So if I give you an electrical circuit, you can actually apply graph theory to actually solve the circuit, right? Understandable? Because in graph theory, you have pretty, what should I say? You have pretty useful techniques that you can actually apply to figure out many complicated things about those fundamental problems through systematic manners, systematic techniques, right? So graph theory would provide you systematic techniques to solve electrical circuits for that matter, right? In fact, graph theory provides you systematic techniques for solving any problem that can be represented as a graph. Okay, it looks like a delta, but yeah, forget that. Someone is saying it looks like a delta, right? Yeah, this is just an example, okay? All right. So let me again make my statement very clear. Any problem that you have in real life that can be converted to a set of vertices and set of edges, that can be converted to a graph like that, right? Maybe you are traveling from one city to another, right? You can solve that problem. You can convert that problem into a problem in graph theory, right? Like that. You have set of vertices or nodes and set of edges, right? Computer network. Right now you're watching this on YouTube, right? And from my computer to your computer, this video reaches through many hops, like 18. I can run a very small program in Linux. It's called traceroute, and through traceroute I can actually see, okay, how this actually is transmitted, right? So it actually hops through many servers, right? Many computers, many points, right? It goes to the local my router first. So I have one router here, then that goes to another router, right? There in another room, okay, and that goes to the router that my ISP provided, okay, and that goes to one of the switches they have, that goes to their server, and that goes to many other server and reaches Google, okay. Then this downstream actually goes to you through a very similar process, right? So you like essentially have 15 or 20 hops before this actually stream reaches you. But question is, how would the computer or how would the network know really which path to take, right? Because as a service, as a streaming provider, YouTube would like to provide you the stream with minimal latency as far as practicable, right? This signal, this stream could go around the entire world and then could come to you, right? But that would be really inefficient. So how would the mechanisms automatically figure out which path to take? Okay, so that's again a problem in graph theory, because all those nodes, all those switches, all those servers can be converted to vertices or nodes like that, and all the connections can be converted to edges, right? And since you can convert this entire problem to a problem in graph theory, there are pretty elegant and powerful techniques in graph theory that you can actually apply to optimize and figure out everything, right? That's just an example, right? All right. So again, anything that you call a network, for example, circuits are also called networks, okay, and computer networks are definitely called networks, right? So graph is synonymous to network, okay. So sometimes graph theory is technically known as network theory, right? All right. So that way, anything that can be converted to a graph is essentially is a candidate for techniques in graph theory that can be actually used to determine various different things. For example, here in the network example, we are looking for the shortest path, okay, in terms of latency, right? Something like that. So there are plenty of techniques. Here in our particular example, we are going to convert this block diagrams into an equivalent graph. That's very important here. So the graph we construct out of a physical problem should be equivalent to the original system, right? Original physical problem. Otherwise, our techniques would be futile, right? So our goal here would be to convert the entire thing into an equivalent graph, so that actually we can apply techniques in graph theory to solve it elegantly, right? That's the point here. And now the thing is, you haven't probably studied graph theory. That is the worst thing about it, right? You haven't probably had a full semester course on graph theory, right? Unfortunate. That was quite unfortunate, right? So unfortunately, simply because of that, I won't be able to actually derive what we are going to do today. Rather, we are going to use a particular formula by a particular electrical engineer that we are going to just tell you and then teach you how to use that, instead of telling you how to actually derive that, how to actually feel about that. But we're going to see what we can do about it, right? But let's start our actual job here, right? Let's take this entire block diagram that we had. Again, during the class, if you have any query, just feel free to ask. All right. So this was our simple block diagram, right? That we actually solved, right? Someone is saying you had graph theory in your third sem. I mean, did you have a proper full semester course on graph theory, or did you just use graph theory in your circuit theory classes? Probably the second one is true, right? All right. Now, with that said, I'm pretty aware of your courses, actually. All right. So let's start our discussion here very quickly. So this is the block diagram we have. Now, essentially, we convert everything to a set of nodes and set of edges, right? Set of nodes and set of connections between them, right? So, of course, nodes are essentially important points here where signals converge or signals diverge from, right? But if I take a signal out of a point, then it becomes, So if I take a signal out of a point, then it becomes a node. Then if signals are summed up at a point, then it also becomes a node, something like that. So with that said, what are the nodes? What are the possible nodes here? For example, this is a node. Is this a node? Yes, it is a node because signal is coming out of it. Question, is it a node? Yes, it is also a node because signals are joining together here. Is this one a node? Yes, this is also a node simply because signals are joining together here, signals are coming out of it as well. So that was true here as well, right? Is this a node? True, this is a node because signals are again joining back in and coming out of it. Okay, things like that, try to understand. Okay, is this a node? Yes, this is also a node because simply try to understand that I am tapping certain signals out of it. Okay, so again, just think about it in terms of circuit theory, right? So this kind of appears to be a node. Is this a node? Yes, true, that's a node. And this node and this node are equivalent, right? This point, this node and this node are equivalent. But still again, we're just going to represent them with two different nodes. But these two are identical. These two are equivalent, basically, the same node. Just a same wire-based connection, right? Nothing else. So we have essentially, right off the bat, we have figured out what nodes there are in this system, right? Right? So there are 1, 2, 3, 4, 5, 6, 7 nodes in this. If you consider this to be a duplicate, then 6 nodes only, right? So again, if you have any query during the discussion, feel free to ask, because there would be a set of bit of queries here in this particular one, because this is not that easy, really. But once you get the hang of it, this would be a very simple process. You would never want to go back to a block diagram reduction ever once you learn this. All right, so let me use a different thing. Okay, so let me just draw the nodes once more. So here is one node, here is this one, I'm just replicating what we have on top there. So essentially these are the nodes, right? We cannot see all of them, but yeah, that's fine. So essentially these are the nodes, right? No problem, right? Okay, right? All right, so let's now fill in the branches, because or rather the edges, right? So otherwise the graph is not complete. So this is kind of, we are constructing a graph out of it, right? A network out of it. And look very carefully what is happening here. Okay, let me use a different thing. Maybe yellow would be nice. All right, so now from this one is X, right? I'm calling it X. Of course this one is Y. So of course I cannot just change the names randomly, right? Like that. So this one is X, this one is Y. All right, so now look at this one. This signal X is going into this summing point here, a summing point or comparator, whatever it is. So this vertex here is denoting a comparator or a summing point or something like that. So this signal is going from this one to this one, right? In this direction. There is nothing difficult to understand. And how much of X is going into this one? Of course the entirety of X is going into this one, right? So I have a gain multiplier of 1. So now here the cost or the weights associated with this directed graph, this is going to a directed graph because we have arrows everywhere, right? So of course signals would flow in a particular direction, right? In an undirected manner, signals never flow, right? Signals will definitely flow from one direction to another. So this is definitely a directed graph and weighted directed graph, because we are doing certain signal manipulation throughout the branches, right? So here this signal X is reaching this summing point without any alteration. So here the weights on this graph are essentially the weights that signals encounter, or rather the gains the signals themselves would encounter, right? Right? So this signal is encountering essentially a 1 gain. So essentially this signal X is reaching this point with a gain of 1, like that. All right. So whatever is the output of this is essentially going to the input of this one, the second one as well. Okay. Through the same gain. I mean, whatever is the output is going as the input of this one. So essentially nothing happens in between these. So this edge, right, this edge also has the same gain. This is essentially also 1. All right, now think about this one. Now think about this one. So from this vertex, or rather this node to this node, if I draw the same connection like that, now we have a problem, right? Let me just all right, now we have a problem, right? So now whatever signal I have here, I'm not denoting anything with anything, right, unless necessary, but try to understand whatever signal I have here. Say let's consider that signal we have here is A. Essentially that signal actually gets multiplied with G1. Of course we are talking in the frequency domain, right? So if the name of the signal is A here, or the value of the signal is A here, and G1 is the transfer function here, then of course I have A G1 as the output of this block. So if A goes into this one, then A G1 comes out of this. In other terms, what comes out of this block, okay, rather this node, what comes out of this node gets multiplied with G1, and then that is fed to this node, right? What comes out of this one is multiplied with G1, and that is fed to the next node. With that information, I can now say that we have a gain of G1 from this node to this node, because whatever comes out of this actually gets multiplied with G1, and then that is fed to the next node, right? So you essentially have that. All right, I think that is, things are becoming pretty clear right now. Then we have a similar connection between these two, and again whatever comes out of this gets multiplied by G2, and that is fed to this point. Okay, so we have essentially G2 here, right? All right, similarly look at this point. Whatever comes out of this point in this direction gets multiplied with G3, and that is fed to this one. So I essentially have G3 like that, right? These are kind of the costs, or these are the transfer functions. So in terms of the graph, these are the weights of the nodes. All right, all right, and now again between this node and these two nodes, the last two nodes, we have a direct connection. So basically whatever comes out of this node actually is directly reflected here. So we again have a direct connection like that, and of course that's a 1. Okay, so no changes are happening, so the signals are directly reflected back in here. So right, someone is saying, someone is asking me to repeat. We shall do another problem, but we shall do another problem. Okay, so but before that let's repeat once more. Okay, so look at the connections. Okay, so here this one is representing this one. Hold on, this one is representing this one. This node is being represented by, sorry, by this one. This one is being represented by this one. This one is being represented by this one. Like that. So between these two, whatever signal comes out of this actually directly goes to this one. So we have a gain of 1. Between these two, whatever signal comes out of this goes into this one. So I have a gain of 1. Between these two, whatever signal comes out of this gets multiplied with G1 and gets fed to this one. So between these two, whatever signal comes out of this gets multiplied with G1 and gets fed to this one. Similarly, between these two, whatever signal comes out of this gets multiplied with G2 and gets fed to this one. Similarly, between these two, whatever signal comes out of this gets multiplied with G3 and gets fed to this one. And between these two, whatever a signal comes out of this gets fed to this one without any alteration. So it's like multiplication with 1. Okay, again we are going to solve a few more problems, so things are going to be clear anyway. All right, now think about the other connections, right? Let's think about the other connections. What other connection do I have? So I have this H1. Question is, what is this H1? This H1 is basically a connection between this point. Let's name these. Who knows? Who cares? Let's call this. Hold on. Let's call these A1, A2, A3, A4, A5. Right. So this is like A1, A2, A3, A4, A5, right? Let's call this nodes, our name for our nodes, right? I'm just naming them, right? Right. So we have a connection that is picked up from A4 and that is fed to A2, fed into A2. With whatever is coming out of this, if the signal is A4, then it becomes H1 into A4, something like that, right? So this signal is being tapped from this one and brought to this one, right? A direct connection exists between this and this. So from A4 to A2, I have a direct connection from A4 to A2 with a gain multiplication of H1, right? So basically whatever signal comes out of this gets multiplied with H1 and gets fed to A2, right? So with that said, we have a connection that kind of looks like this, but there is a problem, right? There is a problem, right? Try to understand at this point. But I mean, the connection is fine, but the thing is, look very carefully. Whatever signal goes in from this, okay, that signal gets subtracted with this one. So we are subtracting whatever signal is coming out of this from whatever signal is going into this one. So essentially, say for example, if this is A, okay, then this signal that is going into this one is H1A, and say this is B, then that is B, fine. So whatever I have here is B minus H1A, right? So that's B minus H1A because we have a subtraction here. But we can think about the subtraction this way. We can think like this is a summing point. Imagine this is a summing point and put a minus sign here. Would that do? Actually, the same thing happens here. If I have B here and A here, then essentially I have minus H1A and that gets added up here. So I have B minus H1A. So the same thing, right? So I can consider this to be a summing point if I just put a minus sign here, right? That's a very simple thing. So all the feedback points can be considered to be summing points if on the feedback transfer function, if we just put a minus sign, right? So now this node is acting as a summing node because whatever signal comes in, it actually sums up all the signals. And since we are just summing everything, then we can just happily put a minus sign here and be done with it by saying that whatever signal comes out of this gets multiplied with minus H1 and whatever I have after that gets added up at node A2, right? That actually gets added up there. All right, so let's clear that discussion. All right. Now think about the same thing here. Okay, let's get rid of the minus sign, huh? And let's all right. All right, let's consider that to be minus 1. All right, now think about this one. Think about this H2 one, right? So here the signal is being tapped from node A5 and that is brought back to node A3. Of course, the same thing, it's a negative feedback, but we can consider this to be a summing point, so everything is summed up essentially. If I put a plus sign here and I put a minus sign there. So if I consider a plus sign here and minus sign here, the same thing is essentially, this is basically a summing point, then this is a negative transfer function like that, right? So with that said, so we are not violating any physics here, right? So essentially we have a connection from A5 to a summing point A3 through a transfer function of minus H2, right? So we essentially have a connection like that through a transfer function of minus H2, right? All right, so that's understood, I think. So from A5 into A3 through a transfer function of minus H2. So whatever signal comes out of this point actually goes through this transfer function which is minus H2 and gets summed up at A3. Essentially we haven't modified the behavior. All right. And with that said, the same thing is true for the last feedback loop. In that one also, I can consider this to be a plus sign here. So I can consider this to be a summing point instead. And here, instead of having a straight up feedback loop with a gain of minus 1, gain of 1, I can consider this to be a gain of minus 1. So whatever comes in here gets multiplied with minus 1 and gets summed up at node A1. Right? Whatever signal comes out of this gets multiplied with minus 1 and gets summed up here, right? So that is also easily considerable like that, right? All right, so this signal gets multiplied with minus 1 and then summed up here. This is the same thing as to saying this signal directly goes into this one and gets subtracted from X. The same thing, right? So, right? So we have a connection between A5 and A1, right? So let's do that. Now drawing this on a drawing pad is pretty difficult. So that's minus 1. So essentially what we have is a signal flow graph representation of the block diagram we had. Again, notice the arrows, they are pretty important. Signals only flow in a particular direction, right? So this is essentially the signal flow graph representation of the entire thing. The entire block diagram we had. All right. All right. And again, I told you, once you learn this one, you would never want to go back to block diagram, naive block diagram reduction, right? All right. So this is kind of the fastest way of doing block diagram reduction. And of course, constructing these signal flow graphs out of the block diagrams is not a difficult task once you get the hang of it, right? Once you figure out what to consider nodes and how to connect the nodes through branches like that, right? So essentially all the costs associated with these branches or edges, they are just the transfer functions, right? Similarly, why do I have 1 here? I can consider that there is a transfer function of 1, connected here. Why do I have 1 here? I can think like there is a transfer function of 1 here, right? Say similarly, what do I have 1 here? I can consider that something like a transfer function of 1. So why do I have 1 here? I can consider that there is a small transfer function of 1 appearing right in between these two nodes, like that. And all the other ones are also transfer functions that are actually not 1, something else. All right, and these A1, A2, A3, A4, these are just the names for the nodes. You can just ignore them. Okay, these are not necessary really. All right, so now if you have any query on how we constructed this one, feel free to ask, because we're going to jump to something called Mason's gain formula to figure out the entire transfer function in a single step. So this was our block diagram. And this is what we call the equivalent SFG, or signal flow graph. So what we have done, we have essentially converted our problem of reducing a block diagram into a problem in graph theory, so that we can apply graph theoretic techniques to actually handle this problem in a more elegant way, without fiddling around with the branches. Where do I move it, like that, without fiddling around everything. We can actually solve this in an elegant way, more elegant way. All right, so please tell me if you have any query at this point. Yeah. Our objective is to figure out the overall transfer function, rather overall gain in this scenario. So our objective is to figure out y by x, the overall transfer function, right? So our objective is to figure out y by x, the overall transfer function. Let me reduce the gain. What is happening? All right. So we are going to do that. Oh, someone is asking, why am I considering 1 everywhere? Okay, again, I think I answered this question. I am considering 1. So between node X and node A1, I am considering 1 here. Simply not because of convention, but because we can happily construct a small transfer function block here and write 1 here. Would it somehow affect our discussion? No, because if this signal reaches this one unaltered, then I can consider that this signal gets multiplied with a transfer function which is 1 and then gets fed to this one, right? So whenever I have 1, we essentially are actually imagining a transfer function of 1 in that path, right? Right? Essentially there is also a transfer function of 1 between these two nodes, right? Right? Out of that we are writing 1, not because of some convention, right? All right. Well, someone is asking why negative sign. I think I explained this in this block diagram. Look very carefully in this nodes. For example, in this node, whatever we are doing, we're just adding the signals. Whatever signals reach a particular node, we are adding things, right? And that's also true when you studied, that was also true when you studied, what is it? Kirchhoff's laws, right? So for example, you knew something like this: the algebraic sum of signals at a particular node, or algebraic sum of currents at a node is equal to 0, right? All right. So you studied that, right? Now, with that simple Kirchhoff's current law, you know that the algebraic sum of signals, or rather currents, from at a particular node is 0, right? So if signals are coming in, then equivalent signals are going to come out, right? Right. Now here, what is happening here? This is a node, but this is not acting like a simple node in a circuit theory problem, right? Imagine that. Why was that point particularly important? That point was particularly important because, now look very carefully. What signal goes into this one? Say let's consider that to be A, for example. Signal A is going into this one. and imagine this to be B, then the signal that is actually reaching this one is H1B. But what is the sum of these two signals? What is the sum of these two signals? Unfortunately, this is not a summing point. This is a comparator, right? A special kind of a summing point. And in this comparator, what is happening? It is comparing signal A with signal H1B. And by comparison, I mean it is subtracting those two signals. So what I have is A minus H1B. Right? But my problem is that for a node, all the incoming signals should be summed up, right? And that should give you the outgoing signal. But how do I represent this addition with a summation? How do I convert this plus, the minus sign with a plus? So if I had a plus sign, I would have no problem there, because this would now become a simple summing point, so that all the signals that come in are added up, and that becomes the output. Okay, very similar to our Kirchhoff's current law. And then in order to cope up with what we had earlier, we instead have to put a minus sign here. So if I get rid of the minus sign from this point, so if I consider that to be a plus, so whatever comes into this node gets added up, then I have to put a minus sign. So signal A is going in and signal minus H1B is going in, so they are added up and they become A minus H1B. But in order to get this one, this transfer function will have to become minus H1B, right? So that this can act as a typical junction or typical node, right? Where incoming signals are added to construct the outgoing signals. So just because of that particular nomenclature, we are considering this to be a simple summing point where signal A is coming in out of this and signal minus H1B is coming in out of this. And how do I get minus H1B? Simply by putting a minus sign in the transfer function itself. Again, so this is kind of a small tweak that we are doing in order to actually represent this as a summing block. So all the signals that are coming in are summed up. So that is reflected here. So this signal coming in and the signal that comes in. So this one actually gets multiplied with minus H1 and it then comes back to this one. That is the mystery of the minus sign, right? And the same thing happens with all the negative feedbacks. So whenever we have a negative sign, we pull that negative sign out of the comparator, okay, into the transfer function itself, so that the comparator essentially becomes a summing block. Right? I believe I answered your question. Again, if you still have some query, feel free to ask. All right. So now we are going to tell you, I'm going to tell you a technique in graph theory that is called the Mason's gain formula that you can actually use to figure out the overall transfer function in a single step. And that's the same single formula. And now I would like to go to the derivation of that formula, but we shall do that in a later class because we shall diverge into many intricate details of graph theory, and then we could actually tell you that how actually this is derived. Okay, so we have something called network flow equations and theories of cut sets and all those things in graph theory. Using those, by solving a few equations, we would actually land up on something called Mason's gain formula. And imagine something for a moment. We are again talking about 1940s. People did not have computers, right? So before Mason invented the Mason's gain formula, imagine what people did. So if you did not have Mason's gain formula, so essentially what happened is, if I give you a big complicated block diagram, you would have no other way to tackle it than doing tedious block diagram reduction, right? Unless you did that, you wouldn't be able to actually reduce the block diagram. So this was very complicated until Mason's gain formula actually came into action, really. With that said, it is a very important point to note. Mason was an electrical engineer guy who knew graph theory very well. What I mean, he was an engineer who understood mathematics pretty well. And throughout this entire history of technology, you would see people who were engineers with good knowledge in mathematics actually did great jobs, right? They're actually remembered. Okay, all those people, all those scientists whose name actually you hear often, they were really good in mathematics as well, right? Those engineers. So then only they could come up with this kind of things that actually simplified the lives of engineers, right? Really. So unless Mason understood how graph theory really worked, he couldn't actually come up with a formula like that and couldn't do anything like that, right? And in fact, all the people that you hear, especially in control systems, signal processing, and subjects like that, they were electrical engineers with excellent knowledge in mathematics, right? So unless you have that, you cannot really excel as an engineer, specifically excel as an electrical engineer. You can never think about that even, right? So, and that's true even today. Unfortunately, mathematics is the most neglected subject in engineering, right? You become engineers without actually having a comprehensive knowledge of mathematics, but that's a very bad thing. Anyway, Mason said that the overall transfer function, which is essentially y by x, the ratio of the Laplace transform or the Fourier transform of the output to that of the input when initial conditions are zero, something that we are going to discuss in the next class. Okay, was given or can be given simply by this formula, and I'm going to explain this, don't worry. So summation mi, or rather let's write mk del k divided by del summation over k. Now that formula might seem pretty difficult at this point, I mean in the beginning, but when I explain this will be pretty easy to understand, I believe, right? Just for the sake of completeness, let me just write down the names. Okay, so mk is the gain of kth forward, hold on, my cat is interrupting, wait a moment. And here is a cat for you. Nice cat, right? Nah. All right. All right. So we are back. We dealt with the cat, right? All right. So mk is the gain of the kth forward path. Delta is kind of tedious. Let me just write down everything. For example, okay, delta is something like 1 minus summation li plus summation li lj minus summation li lj lk plus and so on, like that. Now li equal to loop gain. I'm going to explain everything, don't worry. Loop gain of the ith loop. All right. Similarly, lj is the gain of jth loop, right? li lj is the loop gain product of li and lj if they don't touch each other. and so on. And I'm going to explain all this thing to you. So that is how we define delta, and delta k is equal to delta considering only the loops that don't touch the kth forward path. Oof, huge discussion, right? Let's forget everything and let's go back to the original thing. Let me copy and paste this one. This is just for your reference, okay? And I am going to reduce this drawing a bit so that actually this kind of manageable at least. So that was our simple drawing, right? All right. Now let's first think about MKs. What are MKs? So MKs, those are the forward path gains, I said. Now question is, what is a forward path? A forward path is a path that starts, a path is essentially here, or rather a forward path is a path in this graph essentially which starts from the starting node or the input node. What is the input node? This one. This one is the input node and ends at the output node. Okay, and what is a path? A path is a set of edges so that you do not cross any vertex more than once. So essentially a forward path is a way through which you can start from one node and go to another, right? Without actually going in loops, like without actually crossing one vertex more than once. What do I mean by that? So imagine that example we gave you with cities, right? Imagine this is one city and this is one city. You actually want to proceed from this one and go to this city, right? What is the forward path through which actually you can go there, right? So I can start from here and go to this one, and then of course I can go to this one. Try to understand, because I cannot go to this one, otherwise the path is wrong, right? The direction is wrong. From that, now I can go to this one. Just one more thing before I actually proceed with this. Let me just reduce this drawing a bit. I'm just making the drawing even smaller so that it is just manageable a little bit. All right. Otherwise, it will be very hectic for me. Really. Right. All right. If you cannot see, please let me know. So what happens is, I want to go from here to here, right? Of course, I cannot violate the direction of the arrows because it will not let me go in that path, right? So I can proceed from this one, go to 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 this, and then proceed to this one. So this is the way through which I can actually start from X and end up at Y, right? Look very carefully. And for this particular example, we just have a single graph, a single forward path, right? So is there any other direct way for me to reach from X to Y? The answer is no, really. I just have a single direct way in which I can actually reach from point X to point Y, like that, right? Like that, right? I cannot jump in this way because that will also violate the direction. And one more thing, I cannot cross one node more than once, right? Because that will be like I'm running in a loop, right? I'm coming back to the same city and going from there. That makes no sense, right? So for this, we have a forward path and we write it as M1. And what is the gain of N1? What is the gain of M1? Now imagine a signal that is starting from here. What gain is it encountering? 1, 1. Now it is getting multiplied with G1. So it is getting multiplied with G1, and then that is multiplied with G2, and then whatever we had gets multiplied with G3, and then that gets multiplied with 1, and that reflects at the output Y. My cat is again interrupting. Hold on. All right, sorry for the interruption. All right, so I think you understood this one, right? So we have one directed path actually, starting from one forward path, starting from node X and going to node Y. That's understood, right? So we have that, right? All right. Do I have any other directed paths? No, 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 we don't. Right? Now think about the loops. How many loops I have? All right. Let's think about that. All right. Let's think about the loops, right? Right. All right. Now consider, what is a loop? A loop is essentially a set of branches through which, of course, direction is maintained. Set of branches through which you can start from one node and come back to it without crossing any other node twice. So we are going to start from one node and reach back to it without crossing any other node twice, right? So what are the loops that we can see, right? What are the loops that you can see? So if I start from this node, for example, then I can proceed from this and go in this direction and then come back to this, right? So I can start from this, go through the entire thing and come back to this, right? Right? Look very carefully. I can start from this node, go to this, go to this, go to this, and sorry, is it understandable that I'm going through this and going through this one? Okay, let me make it very clear that we actually understand what we are talking about. So this is the direction we are taking, and from this we are coming back through this one, through this -1, right, and coming back to this. So this is considered a loop. Okay, so what is a loop essentially? A loop is essentially we are starting from one point, one vertex, and coming back to the same vertex without crossing any other node twice, right? So this is like starting your journey from your home and coming back to your home, right? So this is one loop essentially, right? Let's consider that to be loop 1. Okay, and loop 1, and what is the gain for the loop 1? So I started from here. What gain did I see? I saw G1. Then what gain did I see? I saw G2. Then what gain did I see? I saw G3. Then what gain did I see? I saw -1. So this gets multiplied with -1. So essentially I have minus of this one, right? Things will be very clear if I consider the other loops as well. All right, take this one. Do I have another loop? Yes, I do have another loop. For example, if I start from this one, then I can go in this way and come back through this -h1, and that will construct one loop, right? Because we are starting from this point, right? And we are going to this, then we are going to this, and then we are going to come back. That way we are coming back home, right? So here we started from here. All right. So that is your loop number 2. And again, the order in which you consider your loops absolutely does not matter. So you could have thought about this loop later on. In that way, it could have been loop number 3. It wouldn't matter at all. As long as you can figure out all the loops and all the forward paths, you are doing great, really. So I am starting from this point. My signal sees G1, sees another gain G2. So I have G1, G2, and goes back through this. It sees a gain of -h1. So it gets multiplied with -h1. So essentially I have G1, G2, h1 with a minus sign, right? I think these things are pretty easy to understand at this point. With that said, with that said, let's now consider whether we have another loop or not. Yes, we actually have another loop. If I start from this, okay, and think about this, that we are starting from this and going in this direction and then coming back through this loop. I'm making sure that I'm not obscuring anything, right? So I'm starting from this and going through this and coming back to this. So that is another loop, right? And again, the order in which you figure out these things does not matter. Your loop 1 could be my loop 3, does not matter. Now here loop 3, here it starts from this one, it sees a gain of G2 and then a gain of G3 and a gain of minus H2. So essentially I have minus G2, G3, H2. So these are the loops, 3 loops. Right. Right. So now, just to clear up a terminology, what we have here, this forward path, all these loops, they are essentially what is called a subgraph. Okay, a subset of a graph is known as a subgraph. So if I just have this one, this path here, then this is a subset of the original graph. It's called a subgraph. Similarly, all these loops and everything, they are subgraphs. Subgraphs are essentially nodes and edges that are a subset of the original graph. Okay, so those are called subgraphs. So essentially these forward path and these loops, they are all subgraphs of the original graph, right? Original graph essentially here is the signal flow graph we are talking about, right? So here we have that, something like this. All right, so these are the subgraphs. Now again, if you have any query, feel free to ask. Now we have been using this term touch, right? If they don't touch each other, if they don't touch each other, this touching, this term. Okay, now let's clear that up here as well. Okay, so loops are essentially subgraphs and everything. Okay, subgraphs are also graphs themselves, right? So if I just draw this small portion, that also would constitute one graph, right? So with that said, the term touching is used in this context. We say two graphs touch each other if they share a common edge or branch. So in graph theory, we say that two graphs touch each other if they share a common edge or branch, or whatever you want to call it, right? Edge or branch are the same thing, right? So if they share a common branch or common edge, then we say that two graphs are touching each other. If they just share a common node, then they don't touch each other, right? So if they share a common branch, then we say the graphs are touching each other, right? So with that terminology, with all these things, let's calculate delta. All right, so that will be the most difficult task here, really. Calculating delta in Mason's-Gain formula is the most difficult task. And let me assure you, once you learn this technique by heart, what happens is you can look at a very complicated block diagram, and even if I give you a very complicated block diagram, it won't take more than 5 minutes to figure out the transfer function, right? So let's calculate delta. So delta was 1 minus summation Li plus summation Lij Lij minus summation Lij Lk plus and so on. So what it essentially means is that 1 minus sum of individual loop gains plus this term here, sum of the individual loop gain pairs when they don't touch each other. So rather I would use an adjective here instead. Someone is asking something. I will see that. Hold on. Minus pairs, like now triplets. I'm considering. Yes, your question will be answered. Okay, what happens if the loops touch each other, right? We shall see that, right? So now here delta, therefore delta is equal to 1 minus. Let's first calculate the summation Li. What is summation Li? Summation Li is the sum of the individual loop gains, right? So how many loops do I have? I have 3 loops in our particular example, right? I have 3 loops. So it would be L1 plus L2 plus L3. Let's consider that first, right? All right. So now with that said, what do I have? I have 1 minus, in this particular example I have 3 loops, so summation Li would be L1 plus L2 plus L3, right? So now what are L1? What is L1? L1 is this one, L2 is this one, L3 is this one, right? So L1 is minus G1, G2, G3. Do that. So I have minus G1, G2, G3. Now what is L2? L2 is minus G1, G2, H1. So it's minus G1, G2, H1. What is L3 now? L3 is minus G2, G3, H2. Minus G2, G3, H2. Alright? Right? End of story. Now I have loop gain pairs. Now I can now only consider, so that this is the point. Here it says sum of the individual non-touching loop gains. So now this term will only be there if I can find out 2 loops that do not touch each other. Then I have to product their gain and write down, right? Now question is, these are the 3 loops, right? Loop 1 and then loop 2, then loop 3. Question now. So how many pairs can I have? I can have so out of L1, L2 and L3, how many pairs can I have? I have 3 pairs, right? Right? I can have L1, L2, L2, L3, L1, L3, right? Now what about L1, L2? Are they non-touching? Are these loops L1 and L2 non-touching? The answer is no. They are touching each other because they share common branches, right? In fact, more than one common branch. So for example, this common branch is shared. This branch with G1 transfer function is shared. This branch with G2 transfer function is shared. So yes, it has common branches between them. And since having one common branch is enough for them to be touching, end of story. So L1 and L2 are not touching. L1 and L2 are touching each other. So eliminated. L2 and L3. What about L2 and L3? Do they share a common branch? Yes, they indeed also share a common branch. And what is that common branch? That common branch is essentially this G2 transfer function, right? So this G2 transfer function is common between them, right? Right? So L2 and L3 is also highlighted. They also are sharing a common branch. So since they are also sharing a common branch, they are also touching each other. End of story. Okay, so L2, L3, this pair cannot be taken because they are not non-touching. They are indeed touching each other because they share a common branch, which is this G2 transfer function branch, right? Now what about L1, L3? Right? Look at L1 and L3. So if I look at L1 and L3, I can see again the same problem is here. For L1, I have G2, G3, these branches, which are actually shared by L3, right? So again, there are common branches between L1 and L3, namely the G2, G3 branch, right? This G2 branch and G3 branch, these two branches are being shared by L3. So they have a shared or common branch, at least one shared or common branch. So they are also touching each other. So none of the pairs do qualify for non-touching, right? None of the pairs do qualify for non-touching. So I won't have this term here for this particular scenario. Similarly, if if I cannot find two loops that are non-touching, then I of course won't ever find three loops that are non-touching, right? If I can't even figure out if I can't even figure out two loops that are not touching, then how can I figure out three loops that are not touching, right? So that's not possible, right? If all the pairs are touching each other somehow, okay, then of course you cannot find three loops that are not touching each other. So for this particular scenario, that's the end of delta. That's the end of delta. And if I just simplify this becomes 1 plus G1, G2, G3 plus G1, G2, H1 plus G2, G3, H2, something like that. So that's delta. That's delta. Okay. Now all I need to have is delta 1. Look carefully. In the definition here, I have y by x equal to summation mk del k by del. Now here in this particular example, mk is the kth forward path, right? First, second, third, and so on. But how many forward paths do I have in this example? Answer is I just have one forward path. How many? One. So m1, right? So essentially this formula, Mason's gain formula, kind of looks like this. So y by x is the total transfer function. This kind of looks like m1 delta 1 plus m2 delta 2 plus m3 delta 3 divided by delta. But fortunately for our example, I don't even have m2 because there is just a single forward path. So that's cancelled. This is also cancelled. So essentially for our example, what we have is m1 delta 1 divided by delta. So that is your Mason's gain formula for this particular scenario. But question is, what is delta 1? Delta 1, if you go back to the definition here, it says it is the value of delta, but only considering loops that don't touch the kth forward path. So in this example, this would be delta, but we can only consider those loops that do not touch the m1 forward path, right? Very simple. All right. All right. Now let's go back then. What was our m1 forward path? So m1 forward path was this one, right? The first forward path was this one. So this entire set of branches had been taken over by the first forward path. Now I can only consider loops that do not touch the first forward path. I can only consider loops that do not touch the first forward path, right? Question: does loop L1 qualify for that? Answer is no, because L1 and M1 do have common branches, right? So L1 is indeed touching M1. Similarly, what about L2? L2 is also sharing common branches with forward path 1, right? Namely G1 and G2. What about L3? Same thing. With the fast forward path, L3 is also sharing common branches, right? So that way L1, L2, L3, all these are completely out of story when it comes to calculating delta 1. So delta 1 would be the value of delta if L1, L2, L3 did not exist, right? So we have to eliminate those loops which touch the M1 forward path, for example in this one, and all the three loops that we have here are touching the M1 forward path, right? So all these three are eliminated. So loop 1 is no longer there, loop 2 is no longer there, loop 3 is no longer there. Now if I calculate delta, where L1, L2, L3, none of these exist, what will be the value of delta? So L1, L2, L3 do not exist. So what will be the value of delta? Delta would be simply this lonely 1 here, nothing else. Delta would be just 1, right? Because it does not have any loop that does not touch the first forward path M1, right? So these loops are not there anymore, okay, because I can only consider, for calculating delta 1, I can consider those loops only which do not touch the first forward path, in addition to the conditions imposed by the definition of delta itself. So none of the loops are there anymore, so that gets rid of all of this. So I am only left with 1. So delta 1 is essentially 1, and don't worry, we're going to solve more examples on this. So essentially what I have is M1 delta 1 by delta. Now we have calculated everything. So let's first put delta. What was delta? Delta was this one. What do I like to do most? Copy and paste. Nice. Right. Really good. All right. So what about M1? Did we calculate M1? Yes. What was M1? G1, G2, G3. Let's write down. G1, G2, G3. I have to multiply that with delta 1. But what is delta 1? That's 1. Do not do anything. That's the transfer function. And if you go back to the very beginning of our discussion today, in our last discussion, in our last stream, we actually have seen this, right? So this was the original transfer function that we actually calculated by block diagram reduction. And this is the transfer function that we have calculated today through signal flow graph technique, which actually gives you the same transfer function. Now, right at the beginning, the signal flow graph technique might seem a little bit more difficult, but try to understand that this is very systematic. You have a concrete way of tackling the problem, right? And we are going to see the more complicated examples through which this idea would be more reinforced, that signal flow graph would give you an easier way of tackling more complicated problems. Because if you have a more complicated problem, in that case the block diagram reduction technique becomes more difficult, right? Every single step gives you so much calculation and so many things. Now here you are not doing much of a complicated calculations, but instead what you are doing, you are essentially figuring out certain things about the graph and accordingly calculate small bits and pieces, and then at the very end you are just joining all the bits and pieces that you have. So this is computationally much more easier, even though in terms of computational complexity this proceeds factorially. So I'm not going to explain that, but the point is, this is slightly more slightly more systematic, rather way more systematic than block diagram reduction technique, naive block diagram reduction technique. Okay, and once you are familiar and have practiced some problems on this one, a signal flow graph would seem to be the natural way of actually reducing a block diagram. You would never want to go back to simple block diagram reduction unless for trivial situations. Okay, if I give you a block diagram and ask you to calculate the overall transfer function, you would always look for the signal flow graph technique, because that will actually give you an easier way, more often than not, to actually calculate the overall transfer function. And one more important thing, since this is pretty systematic, this can be implemented using a computer program. And as a challenge for myself, I actually implemented signal flow graph reduction technique or signal flow graph technique using C, using C programming language, just to see that I can actually implement this. This is actually so easy that you can actually implement this kind of a technique even in C, right? So this is so systematic, really. Okay, and computers are very good at complicated mathematics but systematic mathematics, right? All right, with that said, this is actually giving you the overall transfer function. Someone is asking, yes, whether delta would proceed with the alternating signs like that, right? Actually, this is in the definition of delta itself. This is in the definition of delta itself. So yes, this is going to proceed like that always, right? All right, so time for another one. Let me go back to what I gave you in the last class, and let me another example, do another example, right? So our discussion so far is over, but we are actually solving another example. So I gave you earlier, so I have to just copy paste, but rather I have to draw it once more, maybe, who knows. Let me draw it. Okay, I have to draw it anyway. So ask me any question that you might have right now. I have somehow blocked this. Okay, ask me any question that you might have. I think we are done. All right. All right. So we also have something like this one coming out of this. And then we kind of have a loop here, right? It is not connecting, they're not joined, right? You cannot just make a ad hoc join like that. You have to either have a summing point or something. So this is not joined. All right, so let me just make this here. I don't know whether you can see what I'm drawing. All right. All right, I believe that was your homework exercise, right? G1. All right, so this was your homework exercise, right? A very big problem, right? Right. So essentially, I mean, it might seem like a very big problem, but it's not really. So we are going to quickly tell you how to actually construct, how to actually solve this using block diagram reduction techniques, right? Because some of you might have some queries on this one, right? So close the file, right? So with that said, let me what I do. Okay, let me do the block diagram reduction on this one. Okay, very easy, quickly. Okay, all right. So first of all, you need to notice that we have a parallel path here, parallel connection here, but unfortunately there is a signal tapping out of this. So unfortunately, if I just add these two up, this point will be removed altogether, right? This point will no longer exist. So all I have to do now is to pull this line somehow out of this one. So either I have to bring this to the right hand side of this one, and or we have to bring this to the left hand side of this one. Now of course, bringing this to the left hand side of this one is easier. Let me copy and paste the drawing. So that was our all right. So have I not written? Okay, what have I done? Hold on, huh? All right, so I mean, this is x and this is y. How much time do I have left? Very quickly I have to write x and y. All right, so with that said, now be patient and look carefully. I have to remove this branch from here to here. Now look carefully. If the signal is here is a, what signal was reaching here? That would have been a g2. So what was coming out of this? What was coming out of this? It would have been a g2 h1. So this signal gets multiplied with h1 and something like that, right? So what I want to do instead of pulling this line out of this, I want to pull the signal out of this so that I can actually construct a parallel path out of there. That's right. That right. So let me just do it here instead. So I'm pulling this out of this point, right? No issue. So what I did, I pulled that branch out of this into this. So now look carefully what the signals were. This was A, this was AG2. So AG2 was going into H1. So if this was H1 before, so that was going into H1 and would have become AG2 H1. Now I just have A going into this one, right? Right? So since A is going into this one, I have to modify this transfer function in order to cope for the changes I have made, in order for the fact that I move this branch from here to here. So A is going into this one. I want this to be on the output, right? A G2 H1. So of course this has to be G2 H1. Very simple, right? It has to be G2 H1. All right. So with that said, Let's copy it. What do I do? And let me paste it once more here, right? All right. Now I have a parallel path here, right? So these two are starting from here and they are summing up here. So I have a parallel connection here, parallel configuration here. So that would be, so I can remove this entire thing with a single block. So some of you have given me a solution, okay, and you can verify whether your solution is correct by this. So now I have that. So just keep in mind that whenever you do any modification, all the points that you are actually losing, or all the junctions that you are actually losing, should not have any relevance anymore, right? So if I did this, so if I did try to see, if I did combine these two, while this line was still here, while the input of this one was still here, and if I did combine these two, I would have a problem. What problem? Simply because by combining these two into a simple parallel block, I would have removed this entirely, right? I would have removed this point entirely. That is not something I can do, right? So now this is a perfectly fine configuration, and while we are at it, without actually drawing it once more, I can actually combine these two, right? Because these are two cascaded block, so this is going to be G4 multiplied by that. So let's combine these two because that's a cascaded block. Let's combine G4 with this. All right, so we have something like that. Very simple. Now again, I do see a feedback loop. But unfortunately, if I take care of the feedback loop right now, this point would be lost. This point would be lost, right? This point would be lost. I cannot have that, right? So I cannot take care of the this feedback loop right now. So what I can do, I can now take this branch and move it to the right. Okay. So this is the only thing you have to remember while doing block diagram reduction. You cannot reduce something that has an internal dependency, right? I cannot consider this feedback loop and write down a single transfer function for the feedback loop, simply because I have an internal dependency. What internal dependency? Because if I construct a equivalent transfer function out of this entire feedback loop, then this point would be lost. So I have to get rid of that first. Then we can actually do the feedback loop configuration, right? So what I can do right now, I can think about this one. I can, instead of pulling this out of this, I can actually bring this to the right hand side. So instead of being here, this line can go its merry way all to the end here, right? Now it's pulling signal out of this. Now say this signal was A. Imagine this signal was A. Someone is asking a question. Yes, I'm going to do that. Someone is asking, can I flip H2 upwards? Of course I can, and that is what we are going to do anyway. Don't worry. Right? We are going to do that. Don't worry. So try to understand that if this is A, then this is going to be A G2 plus G3 into G4, and that is actually now going into this one, right? So instead of this signal being, so when this was just here, this signal was A G2 H1, right? I want that, but unfortunately what I instead have now, A G2 plus G3 into G4 multiplied by this transfer function. So this is not going to be the same, right? I want this output, right? But this is the input now. I want this output. So what should be the transfer function here instead? It's a very simple one. What I can do, I can just reduce the drawing in a proper fashion. So instead, I can now have a transfer function that is the ratio of the output to that of the input. So what is the output? A G2 plus G3 into G4. I have to divide this by a g2 h1, right? So this is going to be g2 plus g3 into g4 divided by g2 h1. So I have that. All right. So there is now one more step that you have to do to understand something very important here, that this point, and this point, rather with different ink maybe, this point, and this point, these are identical points, right? They're the same signal. So this signal is y here. Forget about this one right now. This signal is y here, this signal is y here, this signal is y here. Same thing is going on, right? So instead of drawing it like this, I can just without any calculation, without any complicated calculation, I can draw it like this. Try to understand. I can instead pull this up. See what I'm doing. So look very carefully. So this was H2 going in here. I can pull this wire up here. So that way I would have the same connection but just with a different look. It does not matter because I'm not again modifying anything, right? So with that said, I have what do I have here? I have H2 and that block would come out here. Okay, so what I'm doing, I'm pulling the signal out of this once more and feeding it here. So hold on a second, it has started raining heavily. Hold on a second. All right, so we have that. Now we can construct a simple feedback loop out of this. So once you construct a simple feedback loop out of this, so if you write down the equivalent transfer function out of this and then consider as another feedback loop out of this. So basically what you have to do next is to construct a feedback loop out of this, simplify this, and then you, after writing down the equivalent transfer function out of this, you would have another feedback loop, do that, and then you have the cascade block, do that, then you have another feedback loop, right? So this would be one feedback loop, construct the equivalent transfer function, then after doing that, this whole thing would become a feedback loop, construct an equivalent transfer function of that, then this G1 would be in cascade with that, so multiply, and this whole thing will again be a feedback loop with a feedback transfer function of 1, do that. So that will give you the transfer function of the whole thing. But again, the steps are kind of cumbersome and huge, right? So let's tackle this problem with a signal flow graph technique, right? And this time around, I'm going to do this in a, what should I say, in a shortcut way, right? Let's go back. Let's copy the original problem and do it in a signal flow graph manner, right? So this is the original problem that I have. So again, I'm leaving this entire thing as a homework for you so that you can actually do it yourself, right? So, so that to be followed, right? So, okay, not here maybe, but, all right. So from here, you have to proceed from this point. All right. So now tackle this problem as a signal flow graph technique, right? So the equivalent, or rather, let me just again paste it here. So that was the original graph, right? So let's draw the equivalent signal flow graph. right? Equivalent SFG. So in order to figure out the equivalent SFG, I have to figure out the nodes. I have one node here, one here, one here, one here, one here, one here, one here, and one here, and another here. Okay, and again try to understand that this is essentially this one, the same thing. This is also essentially the same thing. Someone is asking, sir. Okay, someone is asking, can we mix and match graph, signal flow graph and block diagram reduction? Yes, we can. Yes, we can, but I wouldn't suggest it. Right? I wouldn't suggest it because things could become drastically bad very quickly. You might mess up things. Okay. Right? Because signal flow graph requires your undivided attention in this scenario. Because if you make a small mistake, you would have to pay a heavy price. All right, so I think you can still see it, right? Yes, I mean you can mix and match signal flow graph and block diagram reduction, but I wouldn't suggest that. And someone is asking, oh no, fine, it's fine, right? All right. So here we have one node, another node. I'm just drawing them vertically, so that actually nothing is difficult to see. All right. So again, if you encounter an issue, feel free to ask. All right. So now I'm drawing slightly quickly. Okay. So we have one connection from here to here, and that is 1. From here to here, I have G1. If you understood the previous one, I mean, drawing this one won't be difficult. So then I have just poor choice of ink, maybe even poorer choice. All right. I know things are going into my head, so let's remove my head. All right, so I have G1 here, and then we have a direct connection between these two. So here I have 1. Then again, these two are directly connected. So again, that's a 1. These two have a transfer function G2 in between them. These two are directly connected again with 1. These two have a transfer function of G4. These two are directly connected. So I have something like this. All right. All right. Let's construct the feedback loops now. Of course, from this point to this point, I have H1. The same thing we are doing. Okay. We are taking a tap out of the output of G2 and filling it and feeding it back to here, back to this one, right? So, and of course, I am considering this to be a summing point. So I have to put a plus one here, plus sign here, and put a minus sign on in front of H1. So I would instead have a feedback loop that kind of looks like this one. So this would have a transfer function of minus H1, right? Okay, what about this one? This is a feed forward gain here like that. So this is a summation once again. So I'm starting from this point and going into this one, and of course this is already plus, right? So I don't have to worry about it. So this is already plus, so I'm going into this one. So this is going to give you G3. All right, that's going to fade into this one. So again, we just am I correct? No, I don't think I'm correct. Am I correct? No. I think I just started from the wrong one. So this was the one actually I was talking about, right? This was the input of G2, right? So this is the node. So I have to take it from here and feed it back to this one. So this node was actually this summing point. So this was your G3, of course without a minus sign because we already have a plus here. And what about this feedback loop? This starts from the output here. So basically it starts from here, this one, okay, it starts from here and then it goes back to this one, right? So basically this one, and with a gain of minus H2. Of course I am considering a plus sign here and a minus H2. So that's a minus H2. All right, and then we have an overall feedback here like that. So that's again coming from the same point here and going to the first one. Okay, I cannot draw really. All right, so this one is the overall feedback loop, and again, since this has a transfer function of 1, you can imagine there is a transfer function of 1 here, and again if you consider that to be a plus sign, then this becomes a minus 1. Very simple thing, right? So that's a minus 1. So that's the equivalent transfer function of the whole thing. I can now bring my head back. So that's the equivalent SFG of this entire thing, right? So again, if you have any query, feel free to ask. Right. Very quickly. So I don't know how quickly I can actually do it, but let me just try my best. All right. Can you see it? I believe you can see it still, right? All right. Well, let me just increase this a bit. Okay, I think this is fine, right? All right. So figuring out the forward paths. So I'm calculating M1 right now. So what is the first forward path? So starting from this point, going to the end. So this was X and this was Y, right? So this was X and this was of course Y, if I haven't written it earlier, right? So starting from this and going to this one, right? So of course I can proceed through this entire forward path and go like that. So this is my M1. So M1 encounters gain G1, G2, G4. So that's gonna be G1, G2, G4, right? So that is the first forward path. All right. Do I have another forward path? The answer is yes, I have another forward path like this. I'm starting from this point, going to this one. Again, this is X and this is Y. Do I have to write it again and again? Okay, fine. I have another forward path. So which one is, so I'm going up to this point and then I'm taking this route and going to this one. Try to see. So see, I'm not violating the direction of the arrows. So I'm going to this way and jumping over this one and this one. This, see, this is not a feedback. This is again a parallel path that was there, right? So now M2 is another forward path which encounters G1, but not G2, but G1, G3, G4. So that's another forward path, right? So is there another forward path? The answer is no. You can check for yourself, right? Okay, now consider the loops. Okay, again, the order in which you think about the loops does not matter. So I can consider this loop first. So this is one loop. Look very carefully. This is one entire loop, right? Right? So I'm starting from here, going through all of this and coming back. So this is my loop 1. You can consider whatever you want. So what is the gain? I see G1, G2, G4 and then minus sign. So minus G1, G2, G4, right? That's the gain for the loop 1. Consider the other one. All right. Do I have another loop? Yes, I do have another loop. If I start from here, then this is one loop, right? So going in this direction, coming back to this, this is one loop, right? So what is the gain of this loop 2? Again, the order in which you take these do not matter. Okay, so what is the gain of this loop here? So 1, 1, G2 and then minus H1. So this is minus G2 H1, right? What is happening? Why am I pasting this? All right, so now consider another loop. So is this a loop? For example, question is this a loop? No, this is not a loop, right? Because I can go in this way, but I cannot come back in this way, right? So this is not a loop. So that is not there. All right. So question, is this a loop? Yes, this is a loop indeed. Okay, right? So let's consider that to be L3. What are the gains that I encounter? I encounter G2, G4 and minus H2. So minus G2, G4, H2, right? That was one. All right. So do I have other loops? And do I have another loop? The answer is yes, I have another loop, for example. So I can start from this point and go like this one and come back. See, that is one loop. So I can start from here, go through this one, go in this way, and come back like this. So that's another loop. Consider that to be loop 4. Okay, and the gain is, of course, I am not encountering G2, but I am encountering G3. So G3, G4 and minus H2. So minus G3, G4, H2. Okay. All right. Question is, do I have another loop? Yes, I do have another loop, it seems. All right. Okay. Question is, do I have another loop? Yes, I do have another loop. So, which again starts from the beginning, goes this way, and then jumps to this one, goes this way, and then comes all the way back to this one, like that, like that. Okay, so this is my loop 5. Loop 5 encounters the gain of G1, G3, G4 and minus 1. So minus G1, G3, G4. Question is, do I have another loop? So I have exhausted this one, this one. So how many loops? Let me go back then. Okay, so I have exhausted all the loops, I think. So there was one loop throughout the entire thing, 2, so this one loop, 2, 3, 4 and 5. All right, so I have essentially 5 loops, right? So if you somehow make a mistake there, then it's a problem, right? So we have 2 forward paths and 2 and 5 loops in this. All right. All right. So apply Mason's gain formula. So to do that, I have to first calculate delta. Delta is pretty important, right? So delta was 1, again, minus summation of L1 plus L2 plus L3, summation of all the Li's, right? So here it will be L1 plus L2 plus how much? Okay, I have already way over exceeded my time limit. All right. So with that said, again, I would have some other terms like loop pairs, and we're going to see that. So 1 minus So what was L1? L1 was minus G1, G2, G4. So let's write down that. So that's going to be minus G1, G2, G4. What is L2? L2 is minus G2H1 minus G2H1. What is L3? L3 is minus G2G4H2 H2. What was L4? Minus G3G4H2. And what was L5? Minus G1, G3, G4. All right. Then plus, right? So let me just see once again. I just all right. So I've connected all the loops, right? Right. Now with that said, I have to now consider loop pairs which do not share any common branches, right? So all the possible combinations, right? Here, for example, with L1, L2, do they share a common branch? Yes, they do share. So L1, L3, do they share a common branch? They do. L2, L3, do they share a common branch? They do. L3, L4, do they share a common branch? They do. L5, L4, do they share a common branch? They do. So you can, of course, intuitively in your mind, you can figure out. So my point is to now, we have to figure out two loops that do not share any common branch. But unfortunately, all the loops would share some branches, right? All the loops that are there would share common branches, right? At least there is one common branch that is shared by all the loops, which is this one, this small one here, that is represented by this one, this small thing, one, this one. This one is actually shared by all the loops. For example, this is, they are common in L1, this is common in L2, this is common in L3, this is again common in L4, this is common in L5. So there is one branch that is shared by every single loop there. That way, none of the loop, won't be able to figure out any pair of loops that do not touch each other, right? Because all the loops that I have, they share a common branch. They already have a common branch in all of them. That way, none of them are non-touching. So you cannot figure out a pair or a triplet that are non-touching. So again, like the previous one, I do not have any more terms in this particular scenario. So the answer is pretty simple. That would be 1 plus this one plus G1, G3, G4. So that's your delta. And now Mason's gain formula tells you that the transfer function that you have is mk delta k, summation mk delta k. So here would be summation m1 delta 1 plus summation m2 delta 2 divided by delta. Now let me do that and increase the page, right? All right, so now you have to calculate delta 1 and delta 2, right? All right, so what is delta 1? Question is, what is delta 1? Delta 1 is value of delta where I'm considering delta without the loops that touch the first forward path, rather M1, right? So what is the first forward path? This one, right? This is the first forward path. Look very carefully. This is the first forward path. And now I can only consider all the loops that do not touch the first forward path. Now, of course, all the loops would be touching the first forward path, right? All the loops that I have would have some shared branches between them and the first forward path. So all the loops are gone, pretty much gone from the story. And since all the loops are gone from the story, so delta 1 would be simply 1, because all the loops touch M1, right? All the loops would be touching the M1 forward path. All right. Similar to that, what would be the value of delta 2? Again, let's go back. What is M2? M2 is the second forward path, right? Second forward path. So this is the second forward path. And do I have any loop that does not touch the second forward path? The answer is once again no. Every loop that I have here would touch the second forward path. So that way it would be same 1 because of the same condition, because all the loops would touch M2, right? Very simple. Or rather, let me just clear that up. All right. So that way it is also going to be 1 because all the L through L5 are not there anymore. So with that said, the transfer function would simply be this one. So M1 delta 1. So let's go back. What was M1? M1 was G1, G2, G4. That's going to be G1, G2, G4 into delta 1. But what is delta 1? Delta 1 is 1. So multiplying with 1 does not matter. Then plus M2. And now what is M2? G1, G3, G4. So now we now have plus G1, G3, G4. Again multiplied by 1. Does not matter. And then we have divided by delta. But what is delta? Delta is this thing. I wouldn't even dream of copying this. I mean, writing it down. So that is your overall transfer function. So if you did it with block diagram reduction, you would end up with the same result. Now the point you have to understand is that I have drawn all these simply because I want this to be your study material, so you can actually go back and study this. But if I am actually doing this for any practical purpose, I wouldn't even draw this repeatedly, right? I wouldn't draw the signal flow graph repeatedly. And that's true for you as well. You do not have to draw this repeatedly in your exams as well. For example, you didn't need to. And if you are doing any practical job with signal flow graph, you don't need to draw everything repeatedly, right? You just need to calculate these things. Okay, and accordingly, of course, by looking at the loop, for example, I have a loop of minus G3, G4, H2. By looking at that, you would figure out which loop you're actually talking about, right? Because of the transfer functions that are there, right? So that way you don't have to draw everything repeatedly. Just by drawing this, you'll be able to calculate everything and then combine everything together, right? So that way, this is essentially a single step method through which you can, without any cumbersome calculation, you can figure out the transfer function of a whole complicated system. Okay, so I would again suggest you solve this one. And calculate the transfer function accordingly. Okay. Suggest to solve this one through block diagram reduction the way we did it. Do a feedback here, and again feedback, then cascade, then feedback. Do the simplification there, and you shall see that you would end up with the transfer function we have here. All right. So that will be the end of our discussion today. Then, with that said, again, ask any query that you might have here. I'm giving you a simple question here that you would have to construct the signal flow graph out of, and then from there you would have to do the transfer function. You don't have to do the block diagram reduction. Okay. Question is homework here. Again, this is the end of today's class, and just ask any question that you might have. Okay. Homework. A very simple one. I'm not giving you a very complicated one. Okay. Any question that you might have. You don't have to do this using block diagram reduction, but just, or rather, let me just rephrase my question. I'm looking into your question shortly. Let me just draw it first. So this is just a random system out of from my mind. Okay. Fantastic. Someone asking. I mailed you sometimes. Okay, I have seen your emails. They did not land up in the spam folder, but I was busy with something else, so I couldn't actually really check your answers. Sorry for that. I would do that, and in the meantime, try solving it. Try seeing that whether the methodology you used actually is similar to the one I have used. And by now, of course, you can understand that if you do a block diagram reduction, you'll be able to actually verify your result quickly. So that's going to be G1, that's going to be G2, and there is really no point of keeping G1, G2. Just a moment. This is what happens when I pull out systems from the thin air, right? So let's make this G1, make this H1, make this G2, H2, G3. So again, just look very carefully. It's kind of a comparator, but two feedbacks are going into this one. So of course you have to put a plus sign here when you are doing the when you are doing the signal flow graph technique. So here that's going to be a +1 and put a minus sign here. This is going to be a +1 and put a -1 here, and subsequently like that. That's going to be plus, that's going to be minus, and yeah, just like that. So question is calculate the overall transfer function y by x using block diagram reduction technique. Then verify your result using an equivalent signal flow graph. Right, so that will be your homework. All right. So this is apparently a simple one, right? All right. And just before you ask this, let me just make this clear, this thing clear, because you are learning it for the first time. This summing point can actually be split into two summing points, or this comparator can be split into two different comparators. Let me just do that so that actually you can actually solve this, right? Otherwise it will be difficult for you because you are learning it for the first time, right? You know, the summing point we had is equivalent to what I'm drawing right now. So this is kind of equivalent to what I have here. So do this instead, because this will be easier for you to actually cope up with. But this is kind of the same thing. This is exactly the same thing I had earlier. Okay, so if you have combined block like that, you can divide it like that. So yes, so try doing this one. Okay, again, this is a difficult one, but try doing that. All right, so thank you very much for being here, and we're going to end our discussion today. Feel free to ask any question later on via email. I will try my best to answer your questions. Thank you very much. All right, so good day to you, stay safe, and I'll see you tomorrow with Python. Right, all right, thank you.